Okay, hi everyone, welcome back to the Cubical Set seminar. And our first speaker today is Brandon Doherty from the University of Western Ontario, and he will speak about necklaces and cubical categories.
All right, thank you very much for the introduction, Chris. Thanks a lot, everyone, for inviting me here. So today I'll be discussing necklaces and cubical categories and how the left adjoint of the homotopy coherent nerve functor from cubical categories to simplicial sets can be described in terms of necklaces in simplicial sets. So the goal of this project that I've been working on is to obtain a characterization of the left adjoint functor of the homotopy coherent nerve. So this functor, which I'll be writing as Gothic C from simplicial sets to cubical categories, in terms of necklaces in a simplicial set. So the homotopy coherent nerve functor, the traditional simplicial version of that from simplicial categories to simplicial sets, is due to Cordier, and it was this. Its left adjoint has a concrete description in terms of necklaces in a simplicial set, a term which I'll be defining later on. Which was originally due to Duggar and Spivak in a paper of theirs from 2011. So now in their paper on cubical straightening, Kapulkin and Voevodsky generalized the homotopy coherent nerve to the setting of cubical categories rather than simplicial categories. So the goal here is to look at the left adjoint of that functor from simplicial sets to cubical categories and try to come up with an analogous description for that functor in terms of necklaces. So we'll see how that works. So, so as Kapulkin and Voevodsky show in their paper on the cubical approach to straightening, we have this commuting triangle of junctions. So the homotopy coherent nerve factors through cubical categories via this functor where we so we have this functor from simplicial categories to cubical categories that basically applies the right adjoint of the triangulation functor to all of the mapping spaces in a simplicial category. So we can apply that and then apply this cubical homotopy coherent nerve to get the original homotopy coherent nerve. And so then, of course, the left adjoints have a corresponding factorization. So the left adjoint, which I'm writing C delta from simplicial sets to simplicial categories, factors as this functor C from simplicial sets to cubical categories, followed by triangulation on all the mapping spaces. So the hope then is that if we can get a concrete description of this functor, Gothic C, then we could use that to simplify the proof that that the homotopy coherent nerve and its left adjoint form equivalent equivalents using this commuting diagram of adjunctions. So another preliminary thing that I should establish before I get into the details of what I'll be talking about today is that, once again, as with my talk last week, we're working with cubical sets that only have faces, degeneracies, and max connections in the box categories and no other structure maps. And once again, we're going to be writing structure maps on the right when we apply them to a cube. Another thing I should mention before I get into this is that this is a work in progress talk. So the stuff that I've been working on having to do with this is not currently written up anywhere, but hopefully will be in the future. Right, so to begin with, I should define exactly what I mean by cubical category. So by CCAT, I'll be denoting the category of categories enriched over cubical sets equipped with the monoidal structure given by the geometric product. And so what that means that composition in these cubical categories, say composition of maps from X to Y to Z, is a map out of the geometric product of CYZ with CXY into CXZ. And one thing that's important to recall here is that this geometric product for this particular choice of the box category is not symmetric. So it is important that this is a map from CYZ tensor CXY rather than the other way around. It would be a different definition if we had CXY tensor CYZ. So what that means is that in a cubical category, whether we write composition from right to left or left to right really is a substantial aspect of the definition of a cubical category rather than just a style choice. So I'll be writing composition from right to left in this talk. And now, unlike what we would see in, say, a category of categories enriched over a Cartesian monoidal structure, we don't compose two cubes of the same dimension generally to get another cube of the same dimension. Rather, what we do is you compose two cubes in these cubical categories of arbitrary dimension, and then the composite will have its dimension will be the sum of the dimensions of the two things we compose. So here we compose an m cube with an n cube to get an n plus m cube. And the identities in these cubical categories will be 0 cubes in the mapping space from a particular object to itself. So a vertex of CXX in this case, which we compose with cubes to just get the thing you're composing with. So here's an example that kind of illustrates how composition works. So if we have two edges, say an edge G and another edge F, as I've illustrated here, their composite will be a 2 cube. And based on the way that that faces interact with the composition operation, we can work out what the vertices of this cube will be. We can see, as I've illustrated here, that they're all the composites of vertices of the two edges that are being composed here. And the edges of this composite 2 cube are all the composites of either of these two edges with a vertex of the other edge. So we have, for instance, GA and GB, CF and DF. So to make precise what I'm getting at with this picture, we have certain identities that composition in a cubical category satisfies that relate it to taking faces. So if we compose the I epsilon face of F with G, as I've illustrated here, we get the I epsilon face of the composite. And if we compose F with the I epsilon face of G, we get the I plus N epsilon face of the composite. And we have similar identities for computing degeneracies and connections. I won't get into the details of those here, but they just work exactly like what you see there for faces. So here are a few examples of cubical categories. Probably the simplest non-trivial example is for any cubical set X, we have a cubical category that we can call UX, where you just have two objects, X and Y. The mapping space from X to Y is just this cubical set X. And all of the other mapping spaces are either empty in the case of Y to X, or trivial for X to X and Y to Y, by which I mean there's just one vertex and it's the identity. We can view the category of cubical sets itself as a cubical category, using, in this case, the left mapping space from X to Y as the cubical mapping space. So just a reminder of something I briefly mentioned in my previous talk. This left mapping space is defined so that its n cubes are given by maps from box n tensor X to Y. Now, it is important that this is the left mapping space because of the choice of the order of composition. If we were instead composing left to right, then we would use the right mapping space here. And for any simplicial set X, the left adjoint of the homotopy coherent nerve gives us a cubical category that we can write as Cx. And describing these is going to be the main focus of the talk. So I will get to that gradually over the course of the next half hour or so. Right, so we want to show that this functor C is a left Quillen functor. In order to do that, we need to know what the model structure is on the category of cubical categories. So we have this result here, which can be obtained by applying a proposition from higher topos theory, which says that that the category of cubical categories carries a model structure where the generating cofibrations consist of, well, the map from the empty cubical category into the terminal cubical category, so where you just got one object and an identity, together with all of the maps U of the boundary of delta or of box n into U of box n. So those are the so U of cubical set is what I defined on the previous slide, or 2 slides ago or something, where you've just got just that one thing, just that one cubical set from X to Y, and all the others are trivial. And the weak equivalences are the maps, say, F from C to D, which, first of all, are essentially surjective on the categories of path components. So by the category of path components, pi naught C to pi naught D here, what I mean is that for any cubical category, you can obtain a 1 category just by taking the path components of its cubical mapping spaces. So we want the induced map on that to be essentially surjective. And also, each of the induced maps on the cubical mapping spaces should be a weak equivalence in the Grothendieck model structure. So our goal then, to be precise, is to show that C and the cubical homotopy coherent nerve of Kapulkin and Voivodsky form a Quillen equivalence between the Joyal model structure on simplicial sets and this model structure on cubical categories. So one more thing I should say about this, to be precise before I move on, something about this model structure, is the proposition that we've used here is related to the result from higher topos theory that gives a model structure on categories enriched over what Lurie calls an excellent model category. But it's not exactly that proposition, and cubical sets actually don't form an excellent model category because one of the properties that are required by that definition is that the monoidal structure has to be symmetric, which we don't have here. And so in particular, because the category is not excellent, we don't get a characterization of the fibrations from this proposition. I think it should be possible to obtain a characterization of the fibrations by sort of following the argument from Bergner's paper, which constructed the Bergner model structure on simplicial categories, but there are details there that need to be worked out. Right, so in order to show this, in order to show that C is a left Quillen functor, we construct an explicit description of it, which involves necklaces in simplicial sets. So I'll define the basic terminology of those. So we say that a necklace in general is a simplicial set, which we write as a wedge product of of standard simplices here. Now, what we mean by this wedge product notation is that we're identifying the terminal vertex of each of these simplices with the initial vertex of the next one. So we're like taking this string of simplices and joining them together at their endpoints. So we refer to the individual simplices in this necklace as the beads, and these endpoints of them, which we join together, are called the joins. And so then a necklace in a simplicial set X is a map from some necklace like this into that simplicial set X. So here's an example this is what a necklace with 3 two-dimensional beads would look like. So you see we've got these 3 simplices, alpha 1, alpha 2, and alpha 3, where the terminal vertex of each one is the same as the initial vertex of the next. Right, so as I mentioned, there's this concrete description of the simplicial, of the left adjoint of the simplicial homotopy coherent nerve functor, which is given in a paper of Duggar and Spivak. It's also described in a paper of Reel from somewhat later on, which cites Duggar and Spivak's work, and that's actually the description which I'll be quoting here, just because it's a bit easier to work with. Right, so the objects of C delta x for any simplicial set x are just the vertices of that simplicial set. And an M simplex in one of these mapping spaces, say from x to y, would consist of a necklace together with a map from that necklace into the simplicial set x, having x as its initial vertex and y as the terminal vertex, together with an ascending chain of sets, so we have an ascending chain of M sets, where M is the dimension of the simplex, which begins with the set of joins in that necklace and ends with the set of vertices. So these sets are all sets of vertices on that necklace containing all the joins. So what we're hoping to do then is come up with an analog of this description that would describe the version of this functor C that we have for cubical categories, but which would simplify it in some way. So to understand what that description will be, we can take a look at the definition of C delta n, which Kapulkin and Voevodsky have in their paper on straightening. So the objects, as we saw in the simplicial case, are just the vertices of the simplicial set, so the numbers 0 up to n in this case. And the cubical mapping space from I to j is the standard j minus I minus 1 cube, or just delta 0 in the case I equals j, or empty if I is greater than j. And we can view the 0 cubes in these mapping spaces as paths in this post set n from I to j, with higher cubes representing refinements of paths, so ways of going from one path to another by adding additional steps. And composition works by concatenation of these paths, so it's to understand what this is all about, let's look at some examples. So here we have an illustration of the cubical category C delta 2. So in the mapping space from 0 to 1, you can see we have just a single vertex corresponding to the path where you just go directly from 0 to 1. And in the mapping space from 1 to 2, there's a single vertex 1, 2. So those mapping spaces are both box 0. And then the mapping space from 0 to 2 is box 1. So there we have two vertices, 0, 2 and 0, 1, 2, where 0, 1, 2 is the composite of those two vertices, 0 to 1 and 1 to 2. And we have this, this edge between them, which sort of represents, we could think of it as a factorization of that path from 0 to 2 into path from 0 to 1, and then from 1 to 2. So let's look at some higher dimensional examples of these things. So this is an illustration of the cubical mapping space from 0 to 3 in C delta 3. So this is a 2 cube, where the initial vertex is 0, 3. The terminal vertex is the sort of maximal path, 0, 1, 2, 3. And then the two intermediate vertices are the intermediate paths between these things. So the fact that we have this cube of this 2 cube here that fills in that boundary kind of we can interpret that as meaning that we get that it's the same thing whether we first add a step at 2 or at 1 in order to arrive there. So we can do that factorization in either order. And finally, here's an illustration of the cubical mapping space from 0 to 4 in C delta 4. So similarly to what we saw in the previous two cases, the initial vertex of this cube is the minimal path, just directly from 0 to 4. The terminal vertex is the maximal path, 0, 1, 2, 3, 4. And the intermediate vertices are all of the other paths which have some of those stops, but not all of them. So we've been describing this thing in terms of paths in these posets, but an equivalent way to look at those would be as chains of 1 simplices in the nerve of those posets, in other words, in delta n, or in other words, as necklaces whose beads are all one-dimensional. So for instance, the path 0, 1, 3, we can view that as this necklace where we have the edge, delta 3, from 0 to 1, and then the edge from 1 to 3. And when we talk about these edges as representing refinements of paths, we can view those as corresponding to necklaces in delta n. So so we have this 2 simplex here, 1 to 2 to 3, which we can view as sort of representing a factorization of that that path from 1 to 3 into 1 to 2 to 3. And then we can add the edge 0, 1 onto the end of that to get this factorization of 0, 1, 3 into 0, 1, 2, 3, like so. And then composition in these cubical categories, when we view these the cubes as necklaces, just corresponds to concatenation of the necklaces. So the composite, we saw that the composite of 0, 1 with 1, 2 was 0, 1, 2. So we can view that as taking the edges of the simplicial set, which correspond to those vertices, and concatenating them to form a necklace. Now let's look at some higher dimensional examples of that. So here we have a 2 cube, which we are composing with. So we got this 2 cube from 1, 4 to 1, 2, 3, 4. And we're composing that with the vertex 0, 1 to get this composite 2 cube, which goes from 0, 1, 4 to 0, 1, 2, 3, 4. So we view this 2 cube as corresponding to a 3 simplex, in this case delta 4. And the vertex corresponds to a 1 simplex. So this composite then is just the concatenation of that 1 simplex onto the left side of that 3 simplex. One more example of a composition in C delta n. So here we have a pair of edges that are composing to give a 2 cube. And so the way we would view this is each of those edges corresponds to one of these 2 simplices. And the concept we can view as corresponding to this necklace where we've stuck those two simplices together. So what's going on in the 2 cube is that we're taking the path 0 to 4 and sort of factoring that into 0, 1, 2, 3, 4 by like individually factoring 0, 2 into 0, 1, 2, and then also factoring 2, 4. So we have this necklace of these 2 separate 2 simplices, each of which witnesses one of those factorizations. So we have this way of describing a thing of C delta n in terms of necklaces. And so we can basically use the fact that this left adjoint functor C preserves colimits to take that description and extend it to an arbitrary simplicial set. So here's our description then of Cx for a simplicial set X. So the objects, once again, are just the vertices of that simplicial set, the 0 cubes. And for any n, the n cubes in a space of Cx, say from x to y, are necklaces in X whose initial vertex is little x and whose terminal vertex is y, where all the beads, we'll say, are of dimension at least 1. Of course, if you had a 0-dimensional bead, that would be a bit strange because it would just be one of the joins. And then the dimensions -1 of these beads add up to n dimension of the cube. So what this sum formula means here is that each bead of a necklace contributes its dimension -1 to the dimension of the cube corresponding to that necklace. So let's look at some examples then of what kinds of necklaces correspond to cubes of certain low dimensions. So 0 cubes are easy to understand. They're just cubes, or they correspond, that is, to necklaces where all the beads are of dimension 1. So in other words, these are paths from x to y in the simplicial set X. So here are a couple of small examples. If we just have an edge from x to y, say f, as I've drawn it here, then we get a vertex f in the mapping space from x to y. On the other hand, if we have a path consisting of two edges, so g from x to z and h from z to y, then that corresponds to a vertex in the mapping space from x to y, which you write as hg, writing composition from right to left. And this is, in fact, the composite of the vertices that correspond to those two edges. So now the 1 cubes of C, or of these cubical mapping spaces, we think of them as witnessing factorizations of edges which come from 2 simplices in the original cubical set. So say we've got a 2 simplex, as I've illustrated here, where the composite edge is h and the 2 outer edges are f and g. So thinking of this in an infinity categorical sense, we would think of that 2 simplex as witnessing h as a composite of g and f. And so when we translate that into an edge in a cubical mapping space of Cx, what we get here then is an edge from the vertex corresponding to h to the vertex corresponding to the composite necklace f followed by g. And of course, we can also have necklaces where you've got one 2-dimensional bead and then various other 1-dimensional beads. Those will also give you edges. So right here we have a very similar 2 simplex, and we formed a necklace by adding this edge p from x to z onto the end of that. So what that gives us is this composite edge, alpha p, from hp to gfp. So 2 cubes can be described, or can have a couple of different forms. They can come either from 3 simplices or pairs of 2 simplices. So here we've got a 3 simplex that we would think of as witnessing a factorization of this edge r from x to y into f followed by g followed by h, with the 2 intermediate factorizations fq, or qf, and hp. So we get a 2 cube in the cubical mapping space, whose edges witness various compositions of that form. Or, on the other hand, we can have a necklace with two-dimensional beads that will also give a 2-cube. So here we've got these two simplices. So one witnessing H as a composite of F followed by G, and one witnessing R as a composite of P followed by Q. So when we join these together to form a necklace, the 2-cube corresponding to that sort of represents this factorization of RH into Q, P, G, F, where we can either first factor R into QP and then factor H, or factor H and then R second. Right. So how do we compute faces of these cubes? Well, the faces are computed by performing certain operations on the necklaces representing a cube, specifically by taking certain sub-necklaces. So to take the zero face of a necklace, or say specifically a necklace that's just a simplex, so just has a single bead, those will all correspond to the inner faces of that simplex. So right here, for instance, to take the 1, 0 face of the cube, we take the 1, 0 face of that simplex. And so that gives us a well, it's a simplex of a lower dimension, so it corresponds to a cube of a lower dimension, which we can see as a face of the cube up there. Now, for cubes that come from necklaces that have multiple beads, not just a single simplex, well, we'll put composites of necklaces that are just single individual simplices. So to compute the faces of those, we just use the identities that tell you how to compute the face of a composite in terms of faces of the composing factors. And so then it'll just amount to performing these kinds of operations on the individual beads and on one of the individual beads in that necklace. And so the way that we compute the one faces, like die 1, 1, as we have here, is a little bit more complicated. It essentially looks at a particular vertex and then takes the maximal subnecklace, having that vertex as one of its joins. So in this case, we did that with the vertex Z, as you can see here. So we have this necklace, this subnecklace of that simplex, where we got the edge from X to Z, and then this 2 simplex, which has Z as its initial vertex. So now we can also compute connections and certain specific degeneracies by performing operations on necklaces. These we compute by taking certain degeneracies of simplices. So here, for instance, you can see how we compute excuse me, how we compute the connection gamma 1 of this edge by taking a certain degeneracy of the simplex to which it corresponds. And likewise, we would, we have to take a degeneracy, one of these particular degeneracies, or a connection of a composite necklace, something with multiple beads. We would just use the identities for degeneracies of composites. Now, the rest of the degeneracies, so what you call the inner degeneracies, those which are in between 1 and n, those actually don't correspond to necklaces. We have to add those formally. And what we would note here is that these degeneracies and connections which we're able to compute using these operations on necklaces rather than just having to add them in formally, those are exactly the ones which respect the quotient that we take on delta n in order to construct the cosimplicial object Q, which was discussed in various previous talks. So those two facts are related in a way. in a more complicated and technical kind of way, which is involved in the construction here. So one thing I should mention here is that these representations of cubes as necklaces are not unique. So there are certain necklaces which are identified in the sense that they correspond to the same cube. Probably the simplest and most important of these identifications is that we allow ourselves to just omit a degenerate edge from these necklaces, so that the degenerate edges correspond to identities. So if we have this from x to, where you get an edge from x to y, and then just a degenerate edge from y to itself, that's the same thing as, that corresponds to the same cube, I mean, as just the edge from x to y. And if we have, well, there are further identifications that we do between the necklaces that have some of their beads degenerate. I won't get into the details of those now because they're fairly technical. But one nice thing that we can say is that if you have a non-degenerate cube in one of these mapping spaces, which is not an identity, then it does have a unique necklace which represents it, which is totally non-degenerate. So all of the beads of it are non-degenerate. Right, and the only other representatives it could have would be if you just added degenerate edges in different places. So, as I mentioned earlier, there is a characterization of C delta, the left adjoint of the traditional simplicial homotopy coherent nerve in terms of necklaces, and that can actually be seen as a consequence of this characterization that we have of the cubical version of this left adjoint map, together with a certain characterization of triangulation. So if you have a cubical set X, then you can view the M simplices in the triangulation of X as consisting of a non-degenerate cube of X of some dimension n, together with a map from delta m into delta 1 to the n. So where m is the dimension of this simplex. And so to see how this corresponds to that other, or to that description of C delta, recall that the mapping spaces in C delta of X are just the triangulations of the mapping spaces in C of X, where by C of X I mean the cubical C. So if we think about how that lines up with this description of triangulation here, well, the non-degenerate cubes, as I just described in these mapping spaces, correspond precisely to the totally non-degenerate necklaces. And right, maybe I forgot to mention that in my description of C delta in terms of necklaces, but it is assumed that the necklaces there are totally non-degenerate. Sorry, just a second. And the vertices of these cubes correspond to, well, they're sub-necklaces where all the beads are of dimension 1, but we can also view those as corresponding to sub-vertices of the necklaces, which include all of the joins. And so a map from delta m into delta 1 to the n we can view as a path in the poset 1 to the n with m steps, so that will correspond to an ascending chain of sets. Well, I mean, it would be a path on the n cube from the initial vertex to the terminal vertex. And since the initial vertex corresponds to the set of joins of the necklace, and the terminal vertex is the set of all its vertices, then would be an ascending chain of m sets of vertices from which starts at the set of joins and ends at the set of all vertices. So what's useful about this description of C in terms of necklaces is that it makes it, well, relatively easy to show that, that C is a left-Quillen functor. So first of all, we can show that it preserves cofibrations using this description. Right, using this necklace description, we can compute, if we apply C to the boundary of an n simplex, what we'll get is, well, the mapping space from 0 to n will be the boundary of the n-1 cube, and then all the other mapping spaces will just be the same as what the corresponding mapping spaces are in C of delta n. And so from that, we can compute that the map from C delta n, or from C of di delta n into C of delta n is a pushout of one of the generating cofibrations, u of the boundary of the n cube, u of the n-1 cube. So to compute that pushout, basically we fill that boundary in the mapping space from 0 to n. And then normally in computing a pushout in CCAT, we would have to also take some free composites of this new cube with other cubes. But the only composites we would have to add here would be composites with identities, so there's nothing to actually do there. And we have a similar proof to that, which we can use to show that C sends the inner horn inclusions to trivial cofibrations. Those will be pushouts of U applied to a box. And so then, right, so the fibrations between fibrant objects in the Joyal model structure can be described can be characterized by the right lifting property with respect to inner horn inclusions and also the inclusions of endpoints into this simplicial set, which I've denoted E1 here. That's the boundary, or sorry, the nerve of the walking isomorphism. So to complete the proof that C is a left-Quillen functor, it would suffice to show, well, that it sent those endpoint inclusions to trivial cofibrations. And for that, it would suffice to show that C of E1 is contractible in this model structure on cubical categories. And I've also got a proof of that, which proceeds by a somewhat more technical and detailed examination of the necklaces in E1. But it looks as if I don't really have time to get into those details here. So I think maybe this would be a good time to either wrap things up or ask if there's any questions, maybe.
Okay, so first, thank you very much. So please join me in thanking Brendan. And yeah, now we can move to questions and comments. So feel free to unmute yourself or write things in chat and I'll read them.
I'll go first. Firstly, I thought that was really great. I was hoping somebody would do this, so well done. So I have both.
Thank you very much.
I have both a question and a comment. So maybe I'll start with the comment.
Okay.
So I thought about this problem a little bit, sort of whether there are cubical necklaces for a different cube category. So for the Dedekind cubes or the full OSET cubes.
Right.
I guess what's more complicated there is that there are more faces in the cubes because you have these kind of diagonal faces and you've got these symmetries.
Right.
So I have a conjecture of what the necklace characterization is in that context. And it's basically, so for your cubes, your max connection cubes, what you said is essentially an n cube corresponds to a necklace so that the number of vertices of that necklace minus the number of joins is equal to n, basically. And I think in the case where you add in the diagonals and symmetries, what you need to do is kind of like Duggar and Spivak, add additional data, like a flaggy-like thing. But instead of being a flag, I think it's a partition of the set of the set of vertices minus joins. and a partition into n subsets. So that's sorry, what I think an n cube is it's a necklace where now there's a lower bound to the number of vertices minus joins, but it doesn't have to be exactly n. And instead, you have the additional data of a labeled partition into n subsets. So a function, if you like, surjective function from the vertices minus the joins to the set of n things. And kind of the idea is that the partitions into singletons will correspond to these top dimensional cubes, which are the ones that you were seeing here. But then you could permute the singletons, and that will correspond to the symmetries of the cube. Or you could have partitions into larger sets, and that'll correspond to the diagonal faces of one of the maximal cubes. Anyway, if you care, that's a conjecture. I thought it was really interesting, though, that sort of what's going on with the, some of the degeneracies being there, and the max connection being there, but the min connection not really being there. And I haven't thought about that aspect at all. So this might be totally wrong from the point of view of the degeneracies. I'm not sure.
Yes, it was a bit surprising. Well, thank you very much.
So I have a question also, if you don't mind.
Yes, certainly.
So in the for simplicity enriched categories, there's a similar description of the generating cofibrations like the one that you said for cubically enriched categories. So, for simplicity enriched categories, again, they're generated by the inclusion of empty into the point or by these sort of directed suspensions of the boundary of a simplex function. So, I mean, from that description of the generating cofibrations, you can say what the cofibrant simplicity enriched categories are, because it's just the things that you can build out of the generating cofibrations. But there's another description that I prefer, which Dom and I like to call simplicial computad. And I guess my question is, do you know whether there's any sort of, and sorry, whatever simplicial computad means, it's going to capture exactly the cofibrant simplicity enriched categories. So I'm wondering if there's a notion of cubical computad. I think this might be harder to think about in the case where your cubes aren't, the product on the cubes isn't a Cartesian product. I think it, because you're, like, as you pointed out, the notion of a cubically enriched category is a bit more complicated than you'd expect. I don't know. Have you thought about that at all? Do you have any idea what I'm talking about?
Whether there's a cubical analog of, right. So I'm not familiar with simplicial computads. Can you tell me what those are? Like, is there a nice description of them?
Yeah, I mean, I can give you a reference, but sort of what it's for is, I mean, let me just speak for the simplicity enriched case, because this could be wrong for the cubically enriched case. But the necklace description makes clear that there are certain, in like C of X in this, or I guess your C delta of X in these cofibrant simplicity enriched categories, there are certain arrows that are composites of other arrows because the representing necklace has like more than one bead in it. The beads correspond to, and think like the atomic arrows, and then the non-atomic arrows are composites. And so simplicial computad is, I guess, another point of view on simplicity enriched categories, that cofibrant simplicity enriched categories that really emphasizes the sort of atomic ones, the kind of free composites. Anyway, we found that point of view helpful for doing some of these computations effectively, because it kind of allows you to reduce from computing co-limited categories to co-limited graphs, which are like a hell of a lot easier.
I see. Yeah, I'm not aware of any like cubical analog of that that's written up anywhere, or any that's not written up anywhere, I guess. It does sound like something analogous should probably exist. Like, it sounds like this is something that's kind of freely generated by certain, in this case, simplices in the mapping spaces. And I would expect that something similar should be happening for cubical categories. But I'm not aware of any reference for that.
Well, there's definitely not a reference. This is another question / suggestion, something else you could figure out, and if you want to expand the
Right,
discussion.
of course.
So,
Yes, yes, that would be that would be useful too. Thank you for suggesting that.
Okay, we have more questions or suggestions. I'll maybe say very quickly, so that we have 5 minutes for the break, but I'll say very quickly that I think yesterday morning I got my referee report for the Karfolkin-Wojewódzki paper, and the referee suggested going kind of the route that Brandon is going in. So I think I'll need to decline the suggestion in the referee report. But it's good to know that the referee is interested in this work. So I was quite happy with that. Okay, so I suggest that we thank Brandon again for this talk. And then why don't we take a 5-minute break? Or let's take a break until 2 p.m. Pacific. So 5-minute break. Now it's a 5-minute break.
If you want to do 10, that's okay as well.
Let's do 5, and it's better to if we finish early. I don't think. Yeah. Okay. So let's take. So folks, we'll be right back with Martina Rovelli.